So, let's start again our second morning session. It's a pleasure to have with us today Dr. Homer Papadopoulos, who is a functional researcher at NCSR Demokritos and co-founder of the startup Synthesis, living and working in Athens. A natural polymath, Dr. Papadopoulos holds degrees in physics, telecommunications, management, and a PhD in information system science, among others. With over 20 years of research experience, he has submitted numerous papers in various fields, showcasing his expertise in deep understanding of complex subjects, and has created multidisciplinary research programs, consistently pushing the boundaries of innovation in digital technologies. Today, he's going to talk about extracting and managing keys from QKD to enhance cryptographic techniques for file encryption. Dr. Papadopoulos, the podium is yours.
Thank you very much. Thanks very much. I'm trying to configure out how this works. It seems.
Okay, let me turn it on.
It's not working.
Press this button, which is the laser. Does it work?
Okay, perfect. Okay. Yes, thanks very much, Professor Margatos, for the introduction. What we are going to see together is the following. We are going to go through together from zero, to understand exactly few key terms. We will start building our dictionary. And then we will use this dictionary, we will utilize this dictionary in order to be able to get the key from the QKD and then encrypt text, encrypt data, and using PQC to send this data securely and digitally sign this data. So in the first part, so we have two parts. We will work with the dictionary, as you said. We will understand exactly what is symmetric key, what is public asymmetric key cryptography, what is hashing digital signatures and certificates. So we will build our dictionary, and then we will do the demo, and we will start to communicate with QKD and see how using the above terms will help you to get the keys. First of all, I'm coming from Demokritos. Demokritos is the biggest research center in Athens. We are very happy, we are having a new quantum institute. And I'm also co-founder of the spin-off company Synthesis, which we are trying to utilize and exploit business-wise the results of our study. I don't want to stay in this slide because we discussed that yesterday. What I wanted to say in this slide is that we are working in the domain of key cryptography. Okay, no other modes of cryptography, but key cryptography. Key cryptography, because there are code cryptography, etc., is the following. As we said yesterday, we get a key. What is a key? Is a random number. With some tricks, we will show how we get an information, we mix them, and we create this ciphertext. We create something that an adversary is not able to understand. This is what we are doing in cryptography. Why we are doing that? Because this increases the confidentiality of the communication, integrity, authentication, etc. The most simple form of cryptography is the symmetric one. We discussed that yesterday also. Some of the presenters presented symmetric cryptography. What is this? I have a key. I'm Bob. Alice, my friend, is in London. She has a key as well. We have the same key. How we have the same key? We met before somehow. We exchanged the keys with a magic way. And now I get any text I want. I encrypt it, send it to Alice. How? via email, via an application, whatever. And she gets the key and decrypts it, and she reads the message, the information. One of the most famous symmetric keys is the AIS. And how this mixing is happening, I mean, you get the message, you get the key, a number, a big number. You mix them. How this process is happening, there are many ways, hundreds, in fact, of methods of how you can mix keys with text. For example, one of the most known methods we are using, modes we are using, the cipher block chaining. It gets a plain text, it gets a key, does an XOR here, a cipher text, then the output from the first block gets another key, etc., etc. But you can use your imagination here, and you can, let's say, develop your own mode. In our group, we are experimenting some modes. Also, we see here an initialization vector. It's nothing more. It's like a salto. We will discuss with that later. What I wanted to say is that the way you mix, the key with the text can vary between different modes and between different algorithms. Only for AES we see a lot of different modes here, meaning that there are different ways of mixing keys with text. In the software we have developed, in order to send data, to get the key from the QKD and send the data, we are using three main symmetric algorithms, the OTP, the CHA-20, and the AES. Each of these algorithms is being used for different use cases. For example, the OTP is the most secure one. It's an information theoretical secure, meaning that if you have a computer unlimited power, you can't break it. But the problem is that if you have a text of 100 bit, you need a key of 100 bit to do the XOR, meaning that if you have a video of 50 gigabit, you need a key of 50 gigabit. So the question is where you are going to find such kind of key. So this secure method is only for short messages. It's practical for long messages. And we usually use this method for low volume communication, for a message between diplomats or in military. We use OTP to exchange keys between KMS. But the keys for the exchange between KMS is a low volume communication, etc. For example, if you have one page of 1,000 characters in your PC, there is a need for a long key length of almost 8,000 bits, which is quite long. But it's okay, you can find such kind of key. We use CHA, it's another algorithm, another way of mixing keys with information. We use it mainly for video real-time communication, etc. And of course, AES we use that for HTTPS communication, VPNs, etc. When you surf the internet, usually the systems between server and the client using this AES-256, which is the most advanced one. Of course, I have to say that, as we will see, this symmetric key don't have authentication, meaning that you encrypt it and you send it. But how the other side is aware that who is sending the message? In that case, if we want to use these algorithms in practice, we have to use algorithms that do the authentication. For example, for CHATSA we use 1305 for AES, GSM, etc., etc. Here is an example, because let's see exactly how it works and what is a key. Okay, let me do a video. So let's say I have a text, I love crypt, I want to encrypt it. I have to find a key. The first thing I will do, I put a key, a short key. Let's say I put 1, 2, 3, 5 until 0, and then 1, 2, 3, 5. That's it. I encrypt it, and this is the encrypted message. So I get this message, I put it in my email, and I send it the email. The other side gets this encrypted message and gets the secret key. The two parties already have the same keys. Put the secret key there, and we expect to see I love crypt. No, because as you can see, the keys are not the same, so we have to have the same key in order to have the description. This is how AES is working. This is how symmetric thing is working. The issue is that this secret key is very easy to be broken with brute force. I mean, looking for the combinations. So we have to provide this secret key from a device that can ensure that this secret key is random. And that's why we are using QRNG, Quantum Random Number Generation, which is, we assume it's, not assume, it's theoretically proven that it's really random. In your computer, this work is being done by libraries that generate the keys. This IV, which is optional, we use it as a salt in order to create messages that don't generate the same output every time. It's optional, but it's good to use it. The problem with this method cryptography is that, as I said, the secure distribution of the key. Okay, I have met Alice before. We exchanged the keys hand by hand. But if I want to exchange text with George, that is in New York, and I haven't met him for years, how I will do that? So it's an issue how to distribute the keys. And of course, the trust problem, the authentication, because these systems don't provide authentication system. So in that case, we, let's say, invented we came out with a new way of encrypted and exchanging keys. This is the public or asymmetric key cryptography. We have discussed that cryptography a few times in the previous discussions. What is this? In that case, in this cryptography, what you do is that you generate two keys, the green and the red. Always generate two keys. The green is the public key, we call it public key, and the red is the private key. Usually, as you will see, the public is smaller than the private key, which is bigger. And of course, we keep that secret. That's why we use it, we call it secret. And this, we push it to the public, throw it to the public. How we can throw it to the public? If you have a website, you put it in your website. You can put it in your email, or you can give it to your administrator to put it in the server, whatever. But you throw it out there to the world. This is what we are doing. Any one of these 5 users keep the secret key and share the other keys to the public. So all of these people have the public keys of the other entities. Okay, so create 2 keys. I keep the red, push the brown, the public key to the public, to the outer world. Why you do that? For 2 reasons. The first one. So I want to send Alice. Let's say want to send a message to Bob. What Alice has you can consider, we can consider the public key as, say, our card, our business card. We have business card, and we usually use to give these cards to the public. So the public key is like a card. So what Alice has the public key of Bob, because all of the end users here have the public keys of all the other entities. So she gets the public key, she gets the message, encrypted with one of the algorithms, let's say RSA, whatever, and send it to the Bob. Bob gets the message. She has his own private key, and he encrypts. That's the case. So I want to send a message to Ellen. The first thing I have to do is to find her public key, encrypt the message with the public key. I send it. Ellen has her own private key and encrypt it. That's how the public key encryption system works. And encryption, decryption, because Ellen also decrypted. Of course, there is another one step further. Why? Because it's fine to encrypt a message. I love Crete. But if you want to encrypt a video, or you encrypt a book or a big file, this doesn't work because public key cryptography has not been invented to encrypt communication, heavy communication, etc., because it's quite computational expensive method. In that case, what you can do, you can use this public cryptography to together with the text to encrypt the key. This is what the KMS you have seen are doing. What exactly they are doing? They are getting the key, they create a session key, a new key, they encrypt it with the public key, they send it to, let's say, to Bob. Bob gets his private key, encrypt it, and they have encrypt the session. So Alice and Bob have created a trusted session key, and they use this session key to do the previous thing, meaning the AES, SATA, OTP, whatever, to use this to do the symmetric thing. Simple as that. Okay. These are the algorithms. I don't want to get in details with the algorithms. I just wanted to say that usually the RSA, it's a famous algorithm. We use it. It's based on algebra with prime numbers. We select two prime numbers. We do some math, very simple math here, and we create the public and the private key. And we also, another famous algorithm you have seen is the Diffie-Hellman, which is mainly used to exchange the keys. The problem is that, as the previous speakers told us, these are dangerous, is under threat due to quantum computers, because it's very easy for a quantum computer to guess which are the two prime numbers P and Q. This is the main problem. Let's see exactly in practice now how this system, the RSA encryption decryption works. So the first thing we do is that we create two keys. Let's block it here. Hope it will stop. Okay. So who is doing this job? I mean, to create this private public key, you can get a library and it can be done. I mean, it's an issue of your computer, let's say, to do it. So you create a public and a private. You see that the public is always smaller than the public. The public is always smaller than the private. And you can choose how many bits these keys should be, can be. If you choose, for example, 2,000 bits, the output of the keys are bigger. If you choose, let's say, the simple one, 512 bits, these public keys and private keys are smaller. So what we are doing In that case, I want to encrypt, I love crypt, and I want to send it to, let's say, to Bob. But what I have from Bob, I have his public key, because his public key somewhere in the internet can find it. So I get the message, I get the public key. Okay, I copy it, I put it there, I do the encryption. This is the encrypted one. Okay, I get it, I send it through email, for example, or through an application. Bob gets that and has to decrypt it. How? It gets his private key. He's private, he has it there. He put it there, and we expect to see I love crypt here. And yes, hope, yes. And that's it. So this is how it works. So you want to encrypt, take the public key of the other person, encrypt, send it, he encrypted the private key. This is how it works. You want to exchange keys, again, create a new key, encrypt it, send it, the other one with his public key, the other one will decrypt it, and then you have a session key to have symmetric cryptography. So, okay. So, again, this has some issues as well. And the problem is the following. Okay, I get a message from Alice, encrypted. How should I be sure that the message is from Alice? Because my public key is public. So anyone can get my public key, encrypt something, send it to me, and say, I am Alice. So in that case, there's a problem with authentication. And for that, we invented two more tools. The first tool is a digital signature, and the other one we will see is a certificate. So what is a digital signature? The digital signature is a way to authenticate that the message that Alice sent is coming from Alice. How this works? The system works. Alice creates a one hash function. We will see what is this. What is a hash function? To simplify that, if Alice wants to, let's say, sign, because digital signature is about signing, a message I love create, or something like that, or give me 500 euros, it can do it. But if she has to sign a book or a video or whatever, this doesn't work. In that case, you have to create a smaller version of the book, of the video, whatever. So in that case, we have invented hashing. What is hashing? We get some big message, and we create a smaller version of it. So we get the message. Here is a puppy. This is the message, a photo. This can be done with a photo. We create a smaller version, because a photo it has a lot of information. It's a heavy message. We create a smaller information. We hashing. We call this digest. We get the digest. We encrypt it with the private key of Alice, and then we send it to the. We integrated the message, and we send that to Bob. Let's see in practice how hashing is working. This is hashing. So, in fact, what is hashing? I write a text. And the hashing, it's very easy to generate this hashing algorithm in your computer with, let's say, code or something. Let's see how this works. Okay. So I have one letter, I hash it, I get this 256 message. Just a moment to stop it here. The message, if you, in the text, add a photo or a video or whatever, the message will be always 256 bits. This is hexadecimal, it's 64 bits, it's 64 bytes, characters, sorry, each character is 4 bits, so we are talking about 256 bits. So, this is hashing. Get any information and create a very specific output. How we can ensure that, how we can validate the hashing? Sorry. How we validate the hashing? We get the hashing, we put it here, and then we get the text, we put it here, and this should be matched. This is what the other side should do, and we will see the video here. But this is how, in practice, the system is working. LSQCI, if the text is in the other side, from Bob, in the Bob side, for example, we put the same text, and we get the hashing from Alice, this should be matched, because they are using the same algorithm. This is the case. So how the system works with the digital, how Bob decrypts Alice digest. Bob gets the message. It has the message with the same algorithm, so it gets the same digest. Also decrypts the message with, decrypts the hashing with the digest with Alice public key, which is public, and they have, and Bob has two hashes, two digests. This should be matched, and if matched, it means that the message, it comes from Alice. This is how the digital signature is working. Okay, and now let's do a demo in both sides to see exactly how all the system works. So the first thing we have to do is to create, we use the PGP tool. You can go to pgp.org to find the tool, it's easy. The first thing we do is that we are using the two signatures, public and private. This is what we are doing. Okay, Alice is creating public and private key, the same with Bob. Bob creates public and private. This is the first thing you have to do. The second thing, somehow, Alice and Bob should throw to the public, to the outer world, their public keys. This is what they should do. Okay, let's wait for Bob to create public and private. This can be done from external servers, from your computer, from CA authority, we will see later, etc. And you have to give some information to create the public keys. Sorry? Okay. So we get the keys from Alice and Bob. To simplify the demo, and this event, we collect it and we put Bob and Alice private key in the same folder. In fact, they are not in the same folder. One public key, let's say, is in Athens, and one private key is in Athens, where Alice is, and the other private key is in Thessaloniki, where Bob is. But for simplification, we put all in the same folder to simplify the whole thing. And of course, we have a message here. What is the message? Let's see. What is the message? That, let's say, Alice wants to send to Bob. The message is a simple picture. Okay, very simple picture. So Alice wants to send this picture to Bob. What Alice should do? First, this is the message. Okay. Alice has to encrypt the message. How to do it? It gets the public key of Bob. Encrypt the message, encrypt the picture. And then wants to sign. How to do it? It gets her private key and sign through the system we saw with digest, all this hashing digest. Don't worry, you are not going to do it by hand. This is being conducted automatically by the systems, okay, by the applications that are working. So this is how it works. Get the message, get the public key, encrypt it, use your private key, sign it, and this is how it works in practice. So we get the message. Alice wants to get the message. We put it there. We choose Bob's public key. We put it there. And then we want to sign. We choose Alice's private key. We add it there. We use some password for protection issues, nothing more than that. This is the encrypted message. We download it, and we send it via email, for example. Okay. Let's see how the decryption works. First of all, we have the encrypted signed message that I received through email. Bob used its private key to decrypt the message, so to see the dog, the puppy, and it uses Alice's public key to ensure that the message is arrived from Alice. This is how it works. Let's see it in practice. We go there. This is the encrypted message. We put it in the same folder. You get the encrypted message. You put it there, and then you choose Bob's private key to decrypt the message, to decrypt the photo. The password, okay, because when we created the public and the private, we use some password. And of course, we use Alice's public key to ensure that, to decrypt it, to ensure that the message is from Alice. And this is the puppy. This is not the puppy because it's in encoding base 64. In that case, you can use, or your algorithm or your application, you can use a symbol decoder. You put this message there, and this is the puppy. This is how it works. Very simple thing. Okay. Again, still this is not enough because one word is missing, which is trust. What does it mean? It means that if I get a white paper, I put my photo, my data, admin data, my age, whatever, my name, and I sign it and go to the airport and say, here is my data, allow me to take my flight. They will not allow me to do that because, very simple, they don't trust me. Okay, so in that case, we have to invent another entity, which we call them CAs, cryptographic authorities, that they will verify your data. It's the same with your passport, where the certification authority is the government that issues the passport, for example. Okay. So in that case, we created this certification-based authorities that creates a certificate. What is a certificate? You saw previously that what I did is that I put my data and I created the public and private, but this is self-signed system and not authorized and not certified. What I have to do, I have to give this data to an entity, pay, or some entities are free, and they create and they return to me a public digital certificate. For example, the most used one, the X5019, it contains the public key, the user device's name, the name of the certification authority, the date, expiry date, version number, serial number, etc., etc. So instead of going to a library or a tool and create my private and public, what I do, I send my data to these authorities, and they return to me a certificate which includes my public key, and of course, they send to me my private key. This is how it works. Simple. I put the data. We use this request DSR to the authority. I put my data there, etc. How many days the certificate should be public? These are the optional. I don't play with that. And then we generate the certificates, simple as that. And these are the certificates. Let me stop it here. So I get from the certification, from the CA authority, the certification, here it is, this one, which includes the public key. So my public key is here, and this is the private key, and this is the request I did. So this is how the system works. Then I'm going to go through very fast. What do we do with certification? So I consider this is the QKD system, and this is the encryptor, as we will see later. And the encryptor wants to communicate the server. There are one way we do that when we access a website. I want to communicate with you. You are my bank, for example. How can I trust you? show me your certificate with this TLS dialog here. They show me the certificate. I validate the certificate. So I trust this is my bank, and then I put my credentials that I do the job. But what if they want the two systems to exchange data, and also the server wants to authenticate the client? In that case, both the server and the client, they have private and certification. We will not call it public key, we'll call it certification, so private key certification. They show each one's certificates. Give me your certificate. This is mine. Okay, I trust you. This is my certificate. Okay, I trust you. Now let's open a dialogue, and they exchange the data. This is how TLS works. Very simple process. In fact, what we described previously, a client requests access. I want to give me access to your system. Okay, this is my certificate. Okay, this is yours. I trust you. This is mine. I trust you. And we open the channel. And in the TLS, the HTTPS you are using to access the sites, the web. In fact, we are using the asymmetric key, blah, blah, to exchange certificates here. We trust, and then we use the public key to exchange the session key. I mean, the private, the key that will allow me to have this symmetric encryption. So in the HTTPS, first we initiate certificates, the authentication process. Then we exchange the keys, and then we're using these session keys to start working. And now go to the QKD. This is a QKD system, one QKD, two QKD systems over there, and they exchange keys. The issue with the QKD is that they exchange the keys automatically. We trust them, okay, that they already have exchanged the keys securely. Okay, we trust them. And then we have to get the keys. Why we have to get the keys? Because I have to encrypt my data. That's why I want the key. And for that, we are using Encryptor. For those that you are not aware, we are not familiar with encryptors. What is Encryptor? It's a PC. It's a tool. It's a computer, for example, that is able to access QKD and gets the key. And then push it somewhere. For example, in the previous presentation, they presented an encryptor in layer 1. Okay. We created some encryptors in higher layers, etc. For example, if you go to ATM and the ATM is in a kiosk and you put your data there, you have to be aware that the system gets your data. They push the data to an HSM, we call them encryptors, and the HSM sends your data to the bank. So this is the encryptor, a system that gets the keys and does the encryption. Of course, encryptor can be your PC. You can go there by your PC, connect with the QKD, nothing else, talk with the KMS, get the keys, and then encrypt and do it. It's simple as that. I'm talking about KMS because in QKD we have the quantum layer generates the bits. Then we are having the KMS, which does the work. It stores and distributes the keys. And then we have the encryptor. So the encryptor is talking with KMS. And for those that you are not a physicist, I have to say, in the QKD, we have the quantum layer, and above the quantum layer, and above all the layers are engineering layers, are not quantum, are not physics. Okay? So exchange the bits through the quantum system, and then we are having classical, if you like, bits, protocols, etc., classical word to work with the keys. This is how it works, simple as that, because you have seen the ETSI protocol, for example. We will see later how this works. So we have QKD, and we have an encryptor. In our case, we use a very simple encryptor. You can use here a laptop or a box or whatever, or Nokia's, or Evolution Q, I think Evolution Q they used. Okay, so how these systems works, because the encryptor should take the keys from the QKD. How they work, the first thing they have to do is that we have to create certification and private keys here, certified by authority, and certification and the public keys and private keys here, in order to be able to exchange things. So the vendor brings the certification installed there and inform the end user how to create new certificates or send the certificates to be installed in the encryptor. So you need the certificates there. And how the encryptor communicates with QKD as the previous time. In fact, it's the same. Sorry, it's the same process. Here, that a client, a browser is communicating with a browser is communicating with a server. It's the same process, absolutely the same process. We just added a client, e.g. encryptor, Raspberry Pi, etc. Request access to the protected resource, where here is QKD, the server here, QKD KMS server presents certificate to the client, blah, 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 exchange certificates, trust each other, open the channel, and they exchange the keys. And this is no need, I see 5 minutes more, so let's throw it away. So, in fact, because Professor Markatos, because we are having 2 sessions, so I will go through, okay.
Okay, back to back.
So you can add the time because it's quite
update the time, 45 more minutes.
Because all this, the dictionary will be used also the PQC version. Yeah, so.
Thanks.
How this system works, okay. The QKD here, we have the encryptor. And you want to get keys from the QKD. So in order to do that, you have to request new encryption keys. And from the other side, you have to request the QIDs. What is this? What is QKD ID? When a QKD is generating keys, it stores these keys to the KMS. But consider that the number of the keys that is stored there is, let's say, 100,000, whatever. And one QKD, the encryptor here, sorry, the encryptor here gets the key from the QKD. Let's say key number 1. The other encryptor, in order to open their communication channel, has to get the same key. Which key? Somehow you have to inform this encryptor that the number, the key that I got is number 1, the first, let's say, in the stack, or number 2. So each key should have the number in the stack. Okay, so we call that key QKD key ID. So when you request a key, from the QKD, you put this request. It's the famous HC014, etc. It's very easy. Say that Alice, I want to give me keys to Bob. This is the other. And I want a key to 6 bits, and I want 1 key. Maybe you can ask 20. Of course, you have to see the whole description of this API in order to be able to play with these factors and other factors, etc. So, one encryptor sends this command to the QKD. The QKD sends to the encryptor the key and the number of the key. It's number first in the stack, number third, whatever. So this is how the system gets the key. The other side, in order to be able to get the same key and start communication, uses this one, this command, and the other encryptor sends this command to the QKD, saying that QKD2, I got from QKD1 what, and I want to get the keys. And the command is that includes the ID. So the second encryptor sends to the QKD a command saying that I want to give me the second key. And the second key is this QKD. And the response is this. And that's why, and that's how the two encryptors got the same key. Okay. We created this virtual demo. We'll show you how to work. Because we don't have QKD still, we created a virtual simulator QKD system. And we created some clients. We avoided here to work with encryptors, so the encryptor is our PC. That's it. We said that encryptor can be anything. Okay, it's just for the demo. Of course, we add the certificates. We used PFX, I mean a zip format, so we include everything in one file. We want to from you to access either this FTP or this HTTP and download the file, the whole applications we have created for you to play. That's it. If someone wants to do it, we are happy to help you. I mean, Adonis is here. Adonis Korakis is a colleague. So if someone wants to start working with that, please proceed. We created videos of how to do it. So if you don't want now, and in fact now the FTP is not working here because it's the port 21 is closed, but you can download it from here. Anyway, if you wanted to do it from your house with, while relaxing or whatever, all this content will be uploaded in a training platform of ElasticSci, so you can go there and access these tools and start doing exactly what is happening here. What is happening here is that we are installing an FTP client, e.g. file Zilla, and access the FTP client. This is the FTP client, and we put this data in the FTP client. Nothing more than that. Okay. In order to get the information, to get all the tools, or you go to this HTTPS and get the tools. After you do that, after you do that, you have to download the files. So the file for this demo, we call it QKD Etsy client for the Etsy 014 client, and unzip it. This is how this works. So you go to this file, okay, this one, you unzip it, and for those Windows systems that don't have this run time exe file, you have to go to the internet and find it and download it in order to be compatible. It's, this one is not a big deal. Okay, this is how you will do it. It's a step-by-step process. Again, because this system will be used by doctors, we don't expect the doctors to do it. So the system, the final system, will be work automatically. It's just a button. But now we split it in different steps for you to understand how it works. And then, and then after you unzip it, you open this tool over there, QKD exe. And after you run the exe, you will see this application. This one. What this application does, it's an encryptor and decryptor. What exactly it does? It gets keys from the QKD. And the encryptor now is in your PC. And the QKD is in our simulator system. Okay. After you do that, you write here some, for example, how many keys you want to access, 2 or 3. We simplified. In fact, we did a very good, very friendly, user-friendly UI that simplifies this HTTPS request I showed you, which is not very user-friendly. So you add all the information here. In fact, this is the HTTPS, blah, 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 QKD, one, give me. This is the UI here. Okay. And this is how you request key from the ID. Okay, from the other device. The first is the encrypt, and this is the decrypt. So we get the key ID here, we put it here, and we say to the other QKD device, I want the key from this number. Here we have downloaded two QKD keys, and then we download the keys. So this is just an encryptor, a simulator of encryptor, that helps me to access the server and gets two keys from one side and from the other side. And why we do that? We do that because we want to encrypt things. We get the keys to encrypt things. That's why we get the keys. Okay. To encrypt the keys, we created another application. Boom. You will do this thing, and now you have to run this exe, and you will see the application. Here is the application. But in order to run this application, you have to have the keys. And you get the keys from the previous step, which is a simple simulator of an encryptor. So what you do here, you just a simple demo is that you get the keys, you put the keys here, you put your plain text here, and you do the encryption. Okay, and you do the encryption in all the three symmetric algorithms I mentioned to you, OTP, ChaCha, and AES. Okay, and these are the encrypted text. Okay, after you do that, sorry. You just decrypt it. I mean, you keep one of the symmetric. You put there the encrypted text. You put decrypt. The decryptor already has the key IDs, and it does the decryption. This is how encryption-decryption works with QKD keys. It's very simple. It doesn't take. We validate it with non-expert users to go and through this say simulation process, and they did it in 20 minutes easily. Not a problem. Okay. Thank you.